Hey kiddo, welcome back to Linear Algebra 101 Part 4. Today we're going to talk about everything that has to do with a basis when it comes to linear algebra. This is normally the topic in this course where things start to heat up. Things start to pick up and get a little bit more complicated very quickly. So today we're going to take it slow. We're going to explain things. What is a basis? How do you lead up to it? How do you handle questions for it? And what does it mean? All right, so sit back, relax, and let's get you ready. Okay, before we get into a basis, we need to first review what we did in part 3. In part 3, we talked about linear independence, when a set of vectors were known as linearly independent. So let's just state what that was. So if we had a vectors v1 to vk that were in Rn, and c1 to ck were all just real numbers, then if v1 to vk are all linearly independent, this means if c1 v1 plus all the way to ck vk, if a linear combination of these vectors is equal to the zero vector, if they are linearly independent, then this must imply that c1 and ck are all zero. And we call this one the trivial solution. Okay, so linear independence basically means that if you have a set of vectors and you take a linear combination of them, multiply them by another real number, add them to themselves, if that happens to be zero, whatever these set of real numbers are, then if it's linearly independent, you'll then find a way to show that all of these are zero. So as an example, these list of vectors, we'll say 1, 0 and 0, 1 are linearly independent, because if I were to write a linear combination of both of these, I would get that C1 and C2 both have to be 0. So now what happens when something is particularly linearly dependent in it? This is an interesting corollary that comes from the definition of linear independence. So let's say COR for corollary. Let V1 to VK be a subset of Rn are linearly dependent. What this then means is that therefore there exists a Vi in this set. We'll just make this very explicit that it is one of these vectors, such that it can be written as a linear combination of the others, such that Vi is equal to, say, D1 V1 plus all the way to Di minus 1 Vi minus 1 plus Di plus 1 Vi plus 1. We'll just bring this down here, plus all the way to dk bk. So basically, if these set of vectors are linearly dependent, then one of them can be written as a linear combination of the other. One of the ways I like to think of this is I now like to think Vi is technically a redundant vector. Because technically, if every one of these vectors besides vi end up accounting for everything within your space, then why do we even need this to begin with? If vi is a combination of the other vectors, then we essentially don't need it, and we can remove it from it. So let's prove this first, and then we'll get to an interesting theorem that relates linearly dependence to spanning sets. Okay, so what do we need to show? We need to show that if v1 to vk are linearly dependent, then there must exist a vi such that vi can be written as a linear combination of the others. Essentially, we're calling vi a redundant vector. Okay, so let's start. From our definition of linear independence, we said that if all of these are equal to 0, if c1 v1 plus all the way to ck vk, these should be k's, is equal to 0, then this must imply that all of the c1s are 0. That was for linear independence. So now, in the case of linear dependence, this is the opposite, where we need at least one of these to not be 0. So because v1 to vk are linearly independent, we then must have that there exists c1 to ck that are real numbers, where ci is not equal to 0 for some I that is between 1 and k. We don't know which one, but we know there is at least one. Such that c1 v1 plus all the way to ck vk is equal to the 0 vector. Okay, so again, let's look at what the question is asking us. We were trying to find that vi is a linear combination of the others. So let's try to see if we can take vi out of this and bring everything else to one side. So this is going to be equal to c1 v1 plus ci minus 1 vi minus 1 plus ci vi plus ci plus 1 vi plus 1 plus all the way to ck vk. Now let's go ahead and move all of these to the other side. So now we will get that ci vi is equal to minus c1 v1 minus all the way to ci minus 1 vi minus 1 minus ci plus 1 vi plus 1 minus all the way to ck vk. Okay. All right, so we've used the fact that we've now brought vi times ci to the other side and everything else here. Now we're already at a good set because we've got v1, all of the v's besides vi, all of the vectors on this side already. We just need to now pick a d in front such that this will match. However, on this side, we still have ci, which we need to somehow get rid of. Naturally, when we multiply something by a real number, the way we get rid of it is we divide by it. And the only reason we are able to divide by it is because of our assumption of our statement up top. So because ci is not equal to 0, we can now divide everything by ci. So we'll write here, since ci is not equal to 0, this then implies vi is equal to minus c1 over ci v1 minus ci minus 1 over ci vi minus 1 minus ci plus 1 over ci vi plus plus 1 minus all the way to ck over ci times vk. So all we have to do now is find out what d is. So let d, I'll say dj equal to cj over ci for all of the j's, where j is not equal to I. So every single number here, I am now replacing with c1. So for d1, I will now replace with minus c1 over ci. Now we have that vi is equal to d1. This first one is minus c1 over ci, so that's d1 times v1 plus all the way to di minus 1 vi minus 1 plus di plus 1 times vi plus 1 plus all the way to dk vk. And now all we have to do is give our final closing statement. So therefore, there exists d1 di minus 1. Therefore, there exists real numbers d1 di minus 1 di plus 1 all the way to dk such that vi is written as a linear combination here. Okay, so let's review. We stated that if v1 to vk were linearly dependent, that meant there exists a vi such that it was written as a linear combination of the others. We got this because we said if it's independent, then there exists some solution to this one where at least one of those values is not 0. Otherwise, it would just be the trivial solution. After that, we did some rearranging. We brought everything else to the other side. We divided by ci because we know it's not 0. And then finally we set dj to be minus cj over ci, and we got that vi can be written as a linear combination of the other vectors. So now that we talked about this idea of how linear dependence ends up giving us this type of other vector that can be written as a linear combination of the other, for the sake of the rest of the video, we're going to call this vector a redundant one. The idea behind it is that technically if you have these list of vectors and one of them is a combination of the other, do you really need that additional vector? And where this comes in is this idea of linear dependence and spanning sets forming a very interesting connection. So let's show this. So theorem. Let v1 to vk, which are vectors, be linearly dependent. This then exists that there technically is a vi which is written as a linear combination of the other. Now, for the sake of making this a little bit easier for us to do in the proof, I'm just going to change the order of these such that vi is specifically vk. So for instance, if it was the second one that ended up being the combination of the others, I'm just going to move it to the end. One of the ways in mathematics we say that is be linearly dependent such that vi is a combination of the other vectors. So even though I wrote vi here, we are going to rearrange these such that this redundant vector is going to be vk. It's going to be at the end. And the way we write this is basically in mathematics is we say without loss without loss of generality. Now, this is a very fancy way of basically saying we're not going to make any new conditions. We're just going to rearrange it in a way such that the math is going to be a lot easier going forward. So if ever you see a question that says without loss of generality, it really just means they're making it a little bit simpler. They're not adding any new conditions to it. So we'll say I is k. Specifically, this vector is it. So we'll say vk is the vector. Okay, now what does this mean for our statement? This then implies the span of all of the vectors is the same thing as the span of everything without vk in it. Oh, vk minus 1. So the reason we started calling it a redundant vector is that we find if we take the span of all of these vectors and we find that one is written as a linear combination of the other, then the span of all of the vectors is the same thing as the span with that vector removed. Let's go ahead and prove this. Okay, so this is new to us in this series. However, what we have here is technically a span is a set of values. And the way we show that these two sets are the same is we have to do both directions. So let's do that. For the sake of doing this faster, we're going to do backwards first. So I'll do the backwards arrow for this. So we say let x be an element of the span of v1 to vk minus 1. So we're going to assume the right-hand side of this by picking a particular vector that's in here. And then we need to show that x is also within this. Okay, so if something is in the span from part 3, this basically then means that x is equal to c1 v1 plus all the way to ck minus 1 vk minus 1. Where c1 to ck are real numbers. Okay, this one is the easier side. So again, we need to show that this is also a linear combination of these ones. How do we do that? With a very, very simple trick, which you will carry on to do in future questions as well in your course, is that you will then have plus 0 times vk. Right, we can just add a 0 to here, so now I'm going to add it to where I'm doing 0 times the vector vk. So now, if I let ck be 0, this then implies that x is equal to c1 v1 plus all the way to ck vk. Therefore, because we now have a linear combination of these vectors, x is now within the span of x1, v1 to vn. So the right way is done. Now, the little bit more trickier side is we need to show the left way. So, same thing we did when we did the backwards method. We're going to let x be within the span of v1 to vk. And now we need to show that x is also within the span of just v1 to vk. So let's write this out. Okay. This implies there exists a c1 to ck that are real numbers such that x is equal to the sum of c1 v1 plus all the way to ck vk. Okay, so here's where the point of it being linearly dependent comes into play. So we said from the previous proof that technically, because v1 to vk is linearly dependent, vk can be written as a linear combination of the others. Okay, so since, we'll say since vk can be written as, we'll just call these d1 v1 plus all the way to dk minus 1 vk minus 1. Because it is a linear combination of the others, we can then write that x is equal to c1 v1 plus ck minus 1 vk minus 1 plus ck times d1 v1 plus all the way to dk minus 1 vk minus 1. So we're just substituting in for this formula what vk is as a combination of the others. And now, in order to show that it's within the spanning set here, we need some number times each of the vectors. So we're gonna combine like terms for all of the vectors. So that means for v1, we're gonna have c1 plus ck times d1. So c1 here plus these two multiplied together, ck d1 times v1 plus all the way to the end, which is ck minus 1 plus ck times dk minus 1 times vk minus 1. So what we now have is each of these, I will say, be a1, and these will be ak minus 1. So now what we have is a real number, each of these, times each of the vectors. Now we have a linear combination of each of the vectors here that x is a part of. So we say, therefore, x is within the span of v1 to vk minus 1. So again, just to reiterate, what we had to do for the backwards method was really simple. We just added the 0 times vk to it, because technically, because these vectors are just a subset of these, it was fairly easy to show they were. But this direction got a little bit more complicated. We needed to break it down into v1 to vk, and then substitute in the fact that this one was a linear combination, and then we could then find these new ones that we were calling a1 to ak minus 1, such that x was a linear combination of these vectors without vk. Therefore, it is within the span of v1 to vk minus 1. So the reason we started calling vk redundant is that now when we think about spanning sets, it really truly is redundant. That if you have a vk that is a linear combination of the others, you can pretty much just remove it from the set. And that's exactly how we're going to lead into a basis. So let's define what a basis is. So let S be a subset of Rn if v1 to vk is a, if v1 to vk are, there we go, linearly independent. That means there are no redundant vectors. And S is equal to the span of v1 to vk. Then the set of vectors v1 to vk is a basis of S. Okay, so there's two main important things to this question. Is that one, we have that all of these vectors have to be linearly independent, and their span has to be the same as whatever subset you have in there. So let's go through some examples. So example 1. We want to show that the set of 1 and 1 and 1 and negative 1 are a basis for R2. Okay, so from the definition of something being a basis, there's two things we need to show. So we'll put it over here, is that we want to show, one, that these sets, the vectors 1, 1 and 1, minus 1 are linearly independent. And the second thing we need to show is that the span of these vectors, 1, 1 and 1, minus 1, is equal to R2. Okay, so in any type of basis question you're going to have going forward, you need to do these two in order to prove something is a basis. So let's get started. So proof. We're going to prove the first one. So we're going to say let C1, C2 be real numbers such that C1 times V times the first vector plus C2 times the second vector is equal to the zero vector. So before in part 3 we talked about how to solve these. We're going to combine the top and the bottom into their own equations. So we'll have C1 plus C2 equals 0 and C1 minus C2 equals 0. After some rearranging and elimination, we will then find that C1 equals 0 and C2 equals 0. Substitution or elimination will work fine for these, but we'll still find that both of them end with 0. Therefore, these vectors are linearly independent. And now we can move on to the second. Okay, so now similar to the other proof we did before with two spanning sets being the same, or two sets being the same, we now need to do both directions for this one. So proof. We'll do the forward direction first. So we'll say let x be within the span of 1, 1 and 1, minus 1. Okay. Therefore, there exists a C1 and C2 such that x is equal to C1 times the first one plus C2 times the second. Now this one doesn't have a span to it, so this one is slightly different, but still the same idea. Is now I'm going to combine the first ones in the first vector, so I get C1 plus C2 and C1 minus C2. Now in order for this to be within R2, I just need both of these to be real numbers. So I'll say therefore C1 plus C2 is a real number and C1 minus C2 is a real number. Therefore x is within R squared. Okay, so remember the definition we did in part 1, which was in Euclidean space, in these vectors of R squared, all it means is that technically you have something that we could call x1 and x2, that anything within R2 has this form as long as x1 and x2 are real numbers. So because that's what it means to be in R2, that is all we had to show for the forward direction, and we are done. Now we can do the backwards direction. So the backward direction is now going to be, we're going to get let x be an element of R squared. And we want to show there exists a C1 and C2 such that, we want to show that x is within the span of our two vectors, 1, 1, and 1, minus 1. Well, how do we do that? Well, we then need to show that in order to do that, therefore we need to show that there exists a C1 and C2 that are real numbers, such that x can be written as a linear combination of these. So let's try that. So we know what we want to show. We need to find C1 and C2 such that these are combinations. So we will say x is equal to x1 and x2. And now we will have set x1, x2 equal to C1, 1, 1 plus C2, 1 minus 1. And now we just need to find out C1 and C2 in terms of x1 and x2. And we will be good. So we'll say, splitting these up into equations, we'll get 2. So we'll get x1 is equal to C1 plus C2. Those are the top ones. And we'll get x is equal to C1 minus C2 for the bottom. Now you are free to use, again, we want to find C1 and C2. You are free to use whatever method you like for this. For the sake of this video, I'm just going to do elimination. So technically, if I add both of these together, I will then get x1 plus x2 is equal to 2 times C1, and both of the C2s cancel. So therefore, we'll write it up over here. Therefore, C1 is equal to x1 plus x2 over 2. Now if we do the second, where we subtract the 2, we will then get x1 minus x2 is equal to the C1s cancel, and we'll get 2 times C2. So therefore, C2 is equal to x1 minus x2 over 2. Okay, so now what we've done is we've found two real numbers such that we can write any vector that is within R squared as a combination of these two. Therefore, x is within the span of vectors 1, 1, and 1, minus 1. So because we proved the backwards method and we proved the forwards method, we can now write, therefore, the span of our two vectors, 1, 1, 1, minus 1, is in fact R squared. And if we combine this one with the fact we already proved step 1, that it was linearly independent, therefore, let's make some room. Therefore, 1, 1, and 1, minus 1 is a basis for R squared. And that is how we show a particular question is a basis. So let's summarize what we did today. We covered a lot. We talked about linear, we reminded ourselves of linear independence. We then expanded on linear dependence. We then added its relationship with a spanning set, creating a redundant vector. And that, combined with linear independence, then allowed us to show that when you combine linear independence and spanning sets, you get something called a basis. We also went through a particular example of how we can solve those questions where we have to prove a particular set of vectors is in fact a basis. Thank you very much for watching. I hope this helps you a lot in your linear algebra course. Again, please feel free to like and subscribe if you want to see more. And as always, feel free to comment any particular question, any particular topic you would like me to cover on this channel. All right? Good luck, kiddo. You got this.